lot of application stuff. I think somebody had asked me one day, said, what units do I put with this? And we're gonna start to make sure that we're good with that. So, how we determine what units go in there. But guys, section 3.3 today is titled Interpretations of the Definite Integral. Anybody want to volunteer to read my essential question for me here today?
How is the definite integral used to determine units of displacement, and how do you calculate the average value of a function?
Thank you, Ellie. All right, so we're looking at computing displacement, which you guys have done a lot of so far. We've done a great job with this. And then how do you calculate the average value of a function? This is going to be something that's kind of new for you right here, average value. Guys, here's the deal. If I could take all the money from everybody in this room right now and add it up, and I'd say on average, each person has this many dollars. You have $100?
I'm definitely an outlier in that.
I'm on
A
the
low
zero
outlier.
side. I'm a zero.
I intentionally bring my, don't bring my
Actually,
old school in.
I've got negative money. I've got lots of debts I need to pay yet. Okay?
So
Well,
what average are
bring
we
the wall
taking?
half
Are
times
we
and you
taking
don't
the
spend
mean,
money.
the median, and the post? That's different.
We'll just go with me. How's that sound? But if I had to say, let's pool all our money in here, and I want to know what's the average amount of money we have in this room right now per person, what would you do?
You would add it all up and divide by how many people are in it.
Add it all up and divide how many people are in there. Exactly. So like when we add all those bars of area up there, we're gonna find the total area, and then we're gonna divide how wide the interval length is to find an average. That's gonna be a new concept today with integrals, and I'll show you what that means here in a little bit. I'm not sure we'll get all the way through this, but we're certainly gonna try today. So to answer our question today, we need to understand units of a definite integral, and we've kind of had some experience with that when we started talking about how to measure distance using left and right hand sums. New concept today, find the average value of a function. And then we're going to look at some graphs to determine some distance traveled again, but we're going to be comparing it with two separate graphs instead of just one. Okay? So let's make sure we're good on vocabulary. I think most of this stuff should be okay here. Displacement. Guys, displacement is simply the total area bounded by limits and a function. So if this was my graph, maybe this is my function right here, and I have a lower limit A and an upper limit B. Then the total area bounded by the x-axis and a function f of x, along with our lower and upper limit of a and b, would be just this area right in here. Okay? So that is my displacement. We're talking about a total area. Displacement's nothing more than a what, kids? Total area. Okay? All right, we're going to talk about units of an integral. The units we get by taking the units on the y-axis times the units on the x-axis. We've talked about this. So if I had a graph right here that was measured in meters per second, and this was measured in seconds, so we were talking about maybe a left or right-hand bar going up. Guys, if I want the area in here in terms of units, what would meters per second for a height value times seconds for an interval value down there, what would the second units do to each other? So in this particular interval, this would represent a certain number of what?
Meters.
So that area would equal a certain number of meters, right? All agreed there?
Mm-hmm.
Okay. And again, if you don't want to write this down, kids, I know I can print this for you and you can get it that way. So totally up to you, however you want that to work. Okay. And here's the biggie, kids. The average value of a function. Okay. So the average of all point values on a curve from A to B. So here's the deal. Again, if we were talking about money in this room, we would add all the money up, right? And then divide by how many people there are here, right? Or if I want to know the average height of a person in this room, we would take all the heights, add them up, and divide how many people there are, right? Okay, well here's the deal. The average function on something like this, kids, is going to be the following. We're going to have curves that look kind of like this. Maybe they go, I don't know, maybe it goes like this. All right? I want to say, what's the average value of that function from start to finish? Okay? Now when I say right here, guys, what's happening to the values of my function? Like this very beginning point, what's happening to my value each time? It's always increasing, but guys, this is continuously increasing, right? We're not counting for just one spot and then one spot. We're counting for every single spot, all right? And what we're looking to do is to say, guys, is there a line in here that we could draw that if you took the area underneath the curve that we have right here, can you guys kind of see this curve that I have right here? I'll highlight it here real quickly. We're trying to find the height that would give us a situation where this part that's shaded in blue, is the same area as maybe this part shaded in maybe green right here, okay? We're trying to see what y value do I have up here where the area of this rectangle will be the exact same area as that blue shape up there. And this line that's right up here says, okay, the average value of all these points put together, like this might be at 3, this might be at 3.2, this might be at 4, this might be at 7, but all the point values on that line right there, we want to say, what does that average to? What one number does that average to? And it's the same as this horizontal line up here. And we find that by saying, okay, where on this y-axis is the area of the rectangle within this same interval? That rectangle in green is going to be the same exact area as the area in blue. And I'll show you how to do that, okay? Turns out there's a nice little formula for it. Let me write that down for you, okay? Average value is the following. It is the integral from lower limit. Anybody want to guess what I'll put down here? It might be 0 sometimes, but we'll just go a to what?
B.
Of some function f of x. Okay. This is like a total area up top here. This would be like a total area. Then to get to the average, we need to divide that average by how many points we have, or basically the interval length. And the interval length will be found by dividing by b minus a. And we'll look at some examples that involve this right here, okay? But this here is your formula for finding average value. You ever see the word average value or the phrase average value? You're going right to that formula right there, okay? And I'll show you what that looks like here in a little bit. All right, so the one that's really new for you guys is what?
The average value.
Average value. Displacement up there and units, I think you're okay on that. We've seen enough of that so far in the first 2 sections. I think we'll be good with this. But this one right here, that'll be the one that's kind of new for us today. All right? Questions, first page right now. Okay, let's move to the second page. I like these examples today. They're pretty cool. I like them because there's a lot of application here today. All right? So example 1, we're going to go right into this idea of finding average values. Okay? This here says, suppose that C of t represents the daily cost of what? Heating your house. How appropriate. It's winter. Okay? We're going to measure this in what, kids?
Dollars per day.
Dollars per day. Where t is the time measured in what?
Days.
And t equals 0 corresponds to January 1st, 2008. All right? Can I make a sketch of what's maybe going on here? Okay. I'm going to put my little sketch right down here. T was measured how, kids?
Days.
Okay. And then C of t up here, what was this measured in?
Dollars.
Dollars per what?
Per day.
Okay. Now I have no idea what this function might look like. It's January, heating costs, maybe in February, what might happen to costs in February? Going down, and maybe in March it might even go. Okay, so starting from January through March, and I'm going to go through March because my limits go from what to what here, kids?
0 to 90.
0 to 90. You guys agree 90 days is about the first 3 months?
Yeah.
Okay? So I'm just going to say, all right, my graph, in January the temperatures might get, kind of cold out, and then finally maybe it dips down over time like this, okay? I'm going to put a 90 down here like so. Okay. Guys, day 1, you might have a certain cost for that day. And then day 10, you might have a certain cost for that day, whatever it might be. All right? So the first question they ask up here is, interpret this right here. Okay? Guys, isn't this a formula for a displacement of our function C of t over the first 90 days? Okay? So in other words, wouldn't this right in here be the integral from 0 to 90? This area displacement right here?
Yeah.
Wouldn't this area all in here be that right there?
Yep.
Okay, tell me what that means right there. And maybe let me back up. What if we started doing left and right hand sums like we're programmed to do right here? If I had a height measured in dollars for what? Day times an interval length measured in what?
Days.
What would the days units do to each other?
Cancel.
Leaving you with what?
How much money?
So this total displacement's gonna be an area situation where days are gonna go away, so this total displacement's gonna represent the total what?
Money.
Total cost over what?
90 days.
Okay, so right here, what I'm gonna say here first is this. Okay? The integral from 0 to 90 of our function c of t dt represents the total cost over how many days?
90.
Okay, so I don't know. If I was looking at my heating bill or my electric bill that I get, in fact, I think I just got a statement today. Whatever it might be, 200 and some odd dollars, I don't know. But maybe it was $200 in January for this, maybe it was 175 for February, maybe 140 for March. I would add all those totals up, right? Okay, but then if I wanted to know the cost to heat the house per day in the first 90 days, I would take that total cost and divide by what? 90, right? Okay, so this first one right here is simply the total cost, right? Second one that says interpret this, well here, right here, wasn't this part right here, my friends? Wasn't this part right here your total cost?
Yeah.
We're gonna take the total cost, and this is really like 1 times 90 minus 0. This is like 1 over my interval. You know, if you do this, this is like saying the same as dividing by 90 minus 0. When I divide by an interval length, this doesn't become the total cost anymore. It becomes the what? Average cost per day. Okay, so this 1 over, I'm gonna write it a couple ways. 90 minus 0, integral 0 to 90 of c of t dt is really the same as the integral from 0 to 90 of our function c of t dt, which was our total cost up here, right? Over your interval length. This was a total cost, right?
Yes.
This is a certain number of days, right?
Yep.
Wouldn't this be the cost per 1 day when you divide that out then? So this simply becomes my average cost per day. That'll become your average cost per day right there. Right? So the displacement kind of gives you the total throughout the whole interval. And then when I take that total displacement and divide it by the interval length, that gives me the average value each day. Okay? And we'll get some numbers involved here in a bit, but in terms of context, relating total cost and average cost, you understand the difference between the two.
Yeah.
Okay. Next one, finding average values. I'm going to volunteer to read that for me right there.
In the year 2000, the population of Nevada was modeled by the function where P is in millions of people and T is in years. Since 2000, uses function to predict the average population of Nevada between the years 2000 and 2020.
Ay, ay, ay. Aww. Okay, no problem. Might have to use a little decimals with this. Is that okay with you guys? By the way, kids, I found something really cool in decimals yesterday. And I'm going to share it with you on a web page. And I think you're going to kind of like it. You know all the shading part that I was trying to figure out?
Yeah.
I think I figured it out. And it's pretty sweet. Okay. So in 2000 is our starting time, right? P is the number of millions. It says use this function to predict the average population of Nevada between what and what?
2000 and...
Okay, so right here, I'm going to underline this right here. When I see this right here, average in this case it's like an average value, okay? This is automatically telling me go use that formula that says take the integral of your function, divide it by your interval length. Okay, so let's talk about our limits first. Talking years since 2000 and we're going to 2020.
0 to 20.
0 to 20, right? So we're going 0 to 20 on this. This would be the interval length down here, or what minus what?
20 minus 0.
It becomes the definite integral of our function, which our function is 2.020 times what?
1.0.
Okay, now if I'm going to type this in the calculator, I better make sure I put what behind this?
Yeah.
Okay. I haven't shown you guys how to find antiderivatives of exponential functions yet. So if I haven't shown you a shortcut, your idea to figure this out is to go where? Okay, so check this out. This is kind of, I'm kind of excited to show you this. Hopefully I bookmarked it correctly. Please be down there. Oh, definite integral. Have I screwed this up already? All right, are you ready for this? We're going to call this f of x, okay? So help me out with this, friends. What was the original function? 2.0.
0, 2, 0 times 1.039 to the t.
And I'm going to raise this to the x power, okay? Because you got to use x with this in this little formula thing that I've got written here. Okay, but I've got to put what at the end of this?
dx.
Okay, actually I don't, because this is the actual function right here. Now, this dx part's already put in here for you. Is that okay with you guys?
Yeah.
Okay, watch this right here. We want limits to be from what to what?
0 to 20.
Right below here, I've got the antiderivative of capital F of x. So a is down here, b is up here. So I want a to be 0. So I'm just going to come up here and type 0. And I'm just going to go in here and type 20. And looky there, would you? Isn't that kind of cool? Okay. So you can get a visual of what's going on there. And I'm going to use this here for a second with you guys. Now, kids, did that give us a value at all? No. So what you're going to want to do is come down here to the bottom. This at least gives you the visual to see what the graph looked like. Remember yesterday when we had part of that parabola that went below the x-axis and part that was above it to be shaded? This would have been a great thing to have yesterday to see that better, okay? That would have been a really good thing to have to see better yesterday. All right.
How did you figure this out? Did you like YouTube?
I Googled this stuff up, and I actually learned quite a bit of stuff yesterday on prep. It was kind of fun. I get a little geeky and nerdy about stuff like this, but this was cool for me yesterday. Okay. All right, so what you're going to want to do then, we're going to go in and type our actual function in. So if you remember correctly, kids, we're going to functions, and we're going to scroll down to calc to get our little integral sign. I'm just going to type in exactly what we would need. So 0 to 20. Okay, and I'm going to try to remember this. 2.020 times 1.039. Oh, I forgot something's wrong there, isn't it?
Yeah, you got.
Okay, is that better?
Yeah.
And then I'll just go, it doesn't really matter now if you leave it as t or put in x. I'll put in exactly what we've had. But this would be the part, if you want to get a value out, what do you have to put behind it? Okay, what do we get for a value there, kids?
60.68.
Okay, let me just talk to you about what this means, kids. This is not telling you that the population is 60.68 million. What this is telling you, if you would go year by year, so 20 or 2000, population was a certain number. 2001, certain number. 2002, certain number. You keep adding those certain numbers up, If you take the population from 2000 to 2020 and add them up year after year after year after year, so like you take the population at the end of each year, add them up, how many people does it tell you have here?
60 million.
Guys, the initial population was about 2.02 million, right?
Yeah.
I don't think in 20 years you're going from 2 million to 60 million. If you are, that's a problem, okay? That would be like the state of Iowa, like going from 3 million to 90 million in 20 years. I don't think that's gonna happen, okay? But this is simply saying if you take the year population plus another year's population, so these people that have been living in that state for 20 years are accounted for how many times? 20 times, right? So like if Kate was living in Nevada from 2000 to 2020, her census count would count 20 different times on there, okay? So this is how we come up with, well, what was the average population throughout those 20 years? Well, guys, this is the total displacement of all the years of population. If I take this answer now and divide it by, what's the interval length, kids?
20.
What do I get for a value there when you divide it?
About 3.
3 point what? Okay, now watch this right here. I want to show you something, okay? I'm going to type in y equals 3.0343644. My line's not moving, okay? Here's what I want you to understand, okay? This area of displacement in blue right here, kids, you see it?
Mm-hmm.
This red line right here, if you could draw a rectangle from 0 to 20 in a red outline here, the area of this rectangle is the same as the area in blue here. And this tells me that over a 20-year period, the average population of Nevada from 2000 to 2020 was about how many million people? 3 million. 34,000 about.
Yeah.
That
Yeah,
makes
that makes
sense.
sense because it's like you're subtracting that blue shaded region.
Exactly, because this part right here, if you took this part that's an overestimate
It fit
and
right.
put it into the underestimate, it would kind of make that, and that's a great observation right there, okay? So guys, understand this. This gives you the total displacement. And so here's what this is really saying. If you would take every single point, can we count every single point on this line up here? From 0 to 20? No, but we have a way to figure out what the average of all the points on this curve is by doing the total displacement divided by the interval length, and that average value turns out to be that horizontal distance right there. Okay? So average value formula, total integral divided by interval length. If you just call it total integral divided by interval length, that's all you really need to know. So here's what I'm going to jot down back in this. Can you guys remember the numbers for me? What did we get for this first one? When I didn't have 20 there, what was it, like 60 million?
Yeah.
Let me get rid of that 20 again, so we'll see what that looks like. Hey, Mr. Tongas. Okay, so let me get rid of that 20 again, and this goes back to our total integral of, what do we have, 60.68 million? So our total displacement here would have been 60.68 million. And then we divide it by that interval length to get an average population. So let's write this down. Okay, so this total, what did we say that was up there again? 60 point what?
60.68 or something like that.
Million. And then we divide this by an interval length of how many years were we talking about relative to that population sample?
20.
Yep, we were going from 2000 to 2020, so 20 years, okay? So what did we end up with? Did we end up with 3.03 million there?
Yeah.
Let me go back in there and make sure on that. I think I said 3,034,000, didn't I? Yep, because that was the number we put in there, okay? So, average population of Nevada from 2000 to 2020 on a continuous time scale, we could have figured out to be approximately 34,000 people. And guys, this new idea of averages now is coming from your total displacement divided by an interval length right there, right? Okay, total displacement divided by an interval length there. Okay. All right, let's roll on. I have good news. Things kind of get easier after that example. Example 2, units of displacement, and I think you're already pretty good at this. Okay, units of displacement. Okay, it says determine the displacement units for the following definite integrals. We're looking at the integral from 1 to 3 of v of t dt, where v of t is what?
Velocity.
Measured how?
Meters per second.
And t is measured in what?
Second.
I just like to draw a rectangle all the time when I do these. Okay, v of t, that's the dependent axis, so v of t is going to be meters per what, kids?
Meters per second.
This is going to become meters per second times what?
Seconds.
Okay, so if I go meters per second here, times seconds, anything magical going to happen?
Seconds cancel out.
Yep, just like that, they disappear. And we're left with just what here, kids?
Meters.
Meters, okay? So this is going to be the number of meters displaced between what times, kids?
Oh,
1 and
3.
3 seconds, okay? Okay, next one, acceleration in kilometers per hour squared, and t is measured how?
In hours.
As kilometers per hour squared, your science class people, you know that's an acceleration unit, right? We've talked like meters per second squared stuff, haven't you? Okay, so we're talking kilometers per hour squared. Oh, good God. What in the world? Kilometers per hour squared times hours right here. Okay, what's going to happen here, kids?
Well,
1 hour is going to take out 1 right here in the bottom, isn't it?
yeah.
Okay, so we really say, ooh, you said this is like an acceleration, right? The antiderivative of acceleration turns into kilometers per hour, which is like a velocity. Ooh. Okay, apparently I'm the only one excited about that, so hold in mind. Okay, kilometers per hour, so this would be the velocity over the first, from time 0 to time 6, right?
Yeah.
Okay. Next one says 2005 to 2011 f of t dt, where f of t is the rate at which the world's population is growing. So people per what?
Year.
In billions, so billions of people per year, and t is measured in,
Years.
okay? So this is going to be people per year. Times what, kids?
Over year. Or times a year.
So won't this be the number of billions of people?
Yeah.
Oh, where's my O and N? It's not on. There it is, now it's on. Number of billions of people there, okay? Number of billions of people. All right, so if I ask you to say, hey, can you give me a displacement unit given the vertical axis unit and the horizontal axis unit, can you do that?
Yeah.
It's just simply multiplication. It's just like saying, what's the area of this rectangle within a left and right hand sum? Well, that's a base times a height. So you're just taking the horizontal axis unit times the vertical axis unit to see what comes out for displacement there. Okay. Are we cool with that, friends?
Yeah.
Okay, what questions so far? First couple of pages. This is complicated stuff. Are you with me right now?
Yeah.
Okay, let's roll to page 3 here. I think we can maybe get this done today. Let's see. It'll be close. Okay, I really like this next part. All right. Example 3, understanding and comparing displacements. Okay, we kind of talked about this on the last problem of the quick quiz yesterday. Remember we said we've got a particle that starts on the x-axis at 3 and is moving left and right. We found the total displacement to be -6, so it went 6 units left of where we started to end with yesterday.
Yeah.
Okay, this is kind of the same concept right here. Alright? Says let f of t represent a bacteria population which is how many at time 0?
5 million.
Okay, so we're starting with 5 million, right?
Uh-huh.
After t hours, the population is growing at an instantaneous rate of what?
2 to the T.
2 to the t million bacteria per hour. It says estimate the total increase in bacteria population during the what?
First hour.
And then the population at time t equal 1. Okay? I always kind of like to make sketches of this. We know we're starting out with how many million kids?
5 million.
Okay, now, at time 0, I'm just going to make a little graph right here. At time 0, kids, we have that bacteria growing at an instantaneous rate of 2t million bacteria per hour. So if I come up with a function for this, f of t, capital F of t right here, would be your millions of bacteria per hour. So is it okay if I just write bacteria per hour here, kids?
Yeah.
And we're going to measure that over how long? Maybe the better question first is this. We're going to measure the bacteria growth per hour over what time unit? What's the horizontal rate going to be? Hours down here, right? Because isn't t measured in hours right there? Okay, so that's important. So here's the deal, kids. They say estimate the total increase in bacteria population during the what?
First hour.
Okay, so my total growth is going to be the integral from, what are my limits, kids?
0 to 1.
Of my function, which is what?
2 to the T.
All right, so let me jump back into my calculator. We're going 0 to 1, right? That looks pretty good, 0 to 1. Guys okay with that?
Yep.
Okay. I don't know what that is, so what I'm going to do is I'm going to come back down here to get a total value. So I'm just going to type in our actual integral down here. This becomes a definite integral. I think you can just type int in here like that also if you want, guys. Did you know that?
Just type what?
int. Instead of having to search for it all the time, just type int and it'll give it to you.
All in a row?
Yep.
I
Whoop, watch this right here. Watch this. Whoa, what did I do?
Is that like a key on the keyboard?
Nope. Just type int, and then it gives you the integral.
Sweet.
Okay.
It can be lowercase.
Lowercase. Yep. Going 0 to 1, right? And then your function is 2 to the what?
T.
dt, right?
Yeah.
Okay, what value do we get there, kids?
1.44.
Okay, and that would be measured in millions. So how many bacteria were added in 1.44 more, right? Okay, how many did we start with?
5.
5 million. How many more did we add on to that?
1.4.
Okay, so we started with 5. The total integral here then was 1.44 million. Okay, so let's go here. Okay, so this was equal to 1.44 million. So the problem initially started with what?
5 million.
Okay, population starts growing then at 1.44 million more than what we've got. So the total, my friend, would be total growth of 1.44 million would be the 5 million plus what?
Plus 1.44 million.
Which is about 6 point.
for that, you don't want to divide it because it's
Nope,
just.
because it's
for
just
one.
asking for a total. It says nothing about average up there,
Oh.
okay? Now, if I wanted to know what was the average growth in the first hour, you would have divided by a distance of 1, which would have still been 1.44.
Yeah.
But the key word you're looking for is average. If you don't see average in there, you're not dividing. If you see average in there, you're dividing, okay? All right, more about area displacements. This next example, critical. Two cars start from a resting traffic light. My favorite traffic light that I like to use is the one down by the casino coming south headed towards Port City. And people will get in the left lane and they will hammer the gas only to beat you to the gas station area and turn right in front of you.
Exactly.
Never happened to you, I'm sure. Ever. Or has it happened?
Yeah, I have.
I'm in the left lane.
You're the left lane. You're the kind of guy I have road rage with.
No, I'd beat your Chevy easy.
Oh, good God, I knew it was coming.
Don't worry.
Yeah, I walked right into that. All right, Gibby, all right. Are you happy now? You got the, okay, day made? Good.
Yep.
All right, two cars start from rest at a traffic light and accelerate for several minutes, okay? The figure down here is gonna show their velocities as a function of time. Okay, so car one right here is kind of this one that just kind of gradually increases, okay? Car two slowly increases, but what continues to happen to its acceleration? This velocity is picking up, right? We're comparing velocities at a certain time right here, okay? Now, here's the situation, my friends. We gotta answer some questions. Which car is ahead after 1 minute and why? Well, think about this, and I'm gonna jot this down over here again. This velocity over here, what was it? Was it feet per minute that I had up there? I think it was, wasn't it? Yep, feet per minute. So I'm gonna, just gonna make sure that we understand this is feet per minute. So let's just say I'm running a race against Ellie Raffy and we start at the same spot and we run for the same amount of time. Who's probably gonna be further ahead after 1 minute?
Ellie.
Definitely Ellie, okay? If I had to say, how do you know Ellie is ahead, what words or how would you describe how Ellie is ahead, other than I can visually see it? Her speed would be faster.
But what if your speed was faster before mine?
My speed was faster before you, oh, so you're saying the speeds actually swap each other up there?
Yeah, well, because, yeah, I don't know.
She just kept accelerating.
She keeps accelerating.
Kept going.
Acceleration
Okay.
and their velocity would end up being.
Let's talk about this. If we start the race at the same time from the same point and she's ahead, hasn't she gone a longer distance over the same amount of time that I have?
Yeah.
She's gone more distance than I have over time, right?
Right.
Okay. Guys, how would I use this graph up here, feet per minute versus minutes down here to show distances traveled? What would I have to do? Or how would you use those two units, feet per
You have
minute?
to multiply.
Multiply. And if we're multiplying stuff like this, aren't we looking for displacements?
Yeah.
After the first minute, R1 right here, my friends. This is where 1 minute is, right?
Yeah.
Car 1 has only gone a distance equivalent to that area, isn't it?
Yeah.
But wouldn't car 2 be that area plus, or basically, wouldn't car 2 be the
So-
bigger area?
So is it whoever has the bigger area?
Bigger area displacement. In a velocity time graph right here, whoever's got a bigger displacement, that's gonna be further ahead. So which one of these cars, car 1 or car 2, is gonna be further ahead?
Car one.
Car 1 is ahead. Okay, because, and here's why, the integral for car 1, the integral for car 1 from 0 to 1 minute for car 1, that area for car 1 is greater than the integral from 0 to 1 for car 2, isn't it? Isn't that displacement area bigger for car 1 than it is car 2?
Yeah.
How would you figure out how much further ahead car 1 is compared to car 2?
Subtract the areas.
And the area that would be left over would be right in here, wouldn't it?
Yeah.
So if I could find total displacement of car 1 and car 2, this area right here would represent how far ahead car 1 is. That would represent how far ahead car 1 is after how many minutes? 1 minute, right? All right. Which car is ahead after 2 minutes then? Okay, this gets kind of interesting. What happens at this point right here?
They switch.
Not quite switch. At this point right here, this car is, these are all velocities, okay? So at this point right here, the velocities were always higher for car 1 than car 2, but this is the point where they're going the same exact
velocity.
speed. At this point right here then, instead of falling further behind, once this starts overtaking, what starts to happen now?
Car 2 is going fast.
Car 2 is starting to catch up then, right?
Yeah.
Okay, so the question becomes, who's ahead after 2 minutes? So here's the big idea here. Watch this right here. At 2 minutes, and I'm going to do my best to sketch this. Okay. How do I do this? Let's go this way. You guys agree that all the area, if I would stay on the lower lines, if I would go here, and then add in this area right here, oops, I shouldn't have done that. Hang on, I messed that up. Okay, I'm going to call this area 1 down here, or maybe I'll call it area A here. And this area B right here that I've kind of, you agree that area A and area B are both displacements that each car possesses?
Yeah.
Okay? Now, the green area is area for car number 1, right?
Yeah.
Okay? The question becomes then, if these are the same right here, isn't this area right up here something that car 2 went but car 1 did not? So if I shade this a different color, this is going to be another difference in distance, isn't it?
Yeah.
Okay, visually looking at these kids. From minute 1, or I'm sorry, from start to minute 1, whose car was ahead?
Car 1.
Car 1 by that much, right?
Yeah.
But in minute 1 to minute 2, which car went further distance from minute 1 to minute 2?
Car 2.
By that much, right?
Yeah.
The question becomes in the first 2 minutes, which of these areas wins out?
Car 2.
Car 2. So in the whole 2 minutes, who's got more area displacement then?
Car 2.
Because car 1 would be everything down here plus the green, wouldn't it?
Yeah.
Car 2 would be everything down here plus the red. Well, the red's bigger than the green, so what must be true?
Car 2 is.
Car 2 is ahead, and here's my reasoning, okay? We're going to say car 2 is ahead. Because the integral from, now we're not going from 0 to 1, we're going from 0 to what?
2.
The integral from 0 to 2 for car 2 this time, that displacement, total displacement area, is greater than the integral from 0 to 2 of car 1 there. That's some pretty heavy stuff right there, guys. Does the shading help you see the difference though?
Yeah.
Okay, if we're talking velocity time graph right here, the displacements for each vehicle will be the areas under the curve. The parts that I kind of outlined down here are both common areas that they share in the first 2 minutes. This area in green is something that car 2 did not have. This area in red is something that car 1 did not have. So we start comparing the differences in displacements that are not common, and we say, well, the red outweighs the green, so in the first 2 minutes, car 2's ahead. So while Gibby blew me away off the line, I still ran him down and won. Which,
That's why we're only doing a quarter mile.
you know what? You know what? Well, if it's taking me 2 minutes to go to a quarter mile, then you've got issues, buddy. Okay? All right? I might be able to run a quarter mile in 2 minutes on my own feet.
I don't know.
Used to be able to do it 48.9 seconds, but that was a long time ago. Okay? All right. Let's see what the last page says. I don't know if I have time to get through it. I think I'm going to save this last part right here. But this is all average value, guys. It would be the integral of this function divided by what?
5.
It would be the integral of this function divided by what?
3.
Okay, and then what I kind of want to talk about, we kind of talked about with the one example about Nevada. We'll pick this up tomorrow. Hopefully I have a note sheet for you. I'm gonna print this off for you guys to give to you. If you guys want your own note sheet to write stuff in, cause you don't like the way stuff is written on mine, I can provide you with that, but I am gonna stop there.